Okay. Okay, so today we wanted to talk about electromagnetic induction. And what happens is we use devices, magnetic fields, wires, batteries, to produce um, voltage current and work with that to supply the current to power things. Magnetic flux is simply the product of the magnetic field and the total area of whatever coil or wire that we're trying to have the magnetic field lines pass through. Faraday's law says that the size of the induced EMF, which is just nothing more than a voltage, is proportional to the rate of change of flux through the coil space. And there are a lot of ways in which the magnetic flux can change. We can change the area. We can change the angle between the area and the field. We can change the field over a period of time, so there's a lot we can do. And we use electromagnetic induction when we use generators and transformers. And then Lenz's law governs the direction of the induced EMF or current in the device, and the induced EMF or current must always oppose the change that produced it. So we look at some formulas. When you talk about the flux, and I'll show you a little bit about that. And this right here is the Greek letter phi, and the little m is for magnetic, so magnetic flux is equal to the field strength, which is B, times A, times the cosine of theta, which is the angle between B and A. And if the field is parallel to the plane of the area, the angle is 90 and the flux is 0. If it's perpendicular, then you get all of the lines passing through, the field lines passing through that particular surface area, and you get maximum flux. And the change in flux over time is what sets up the EMF or the voltage. And this negative sign simply tells us that the induced EMF is going to oppose the change which produced it, so don't worry a whole lot about the negative sign. We'll talk about that. And then we take this equation and rewrite it in terms of BA cosine theta, because if you look at it, this phi right here is really the same thing as BA cosine theta. Capital N is the number of turns in our coil, typically 1, but it doesn't matter if it's 20, we multiply by 20. Now, we can come up with an expression for the voltage due to some kind of motion somewhere. And we've got a wire of length L being pulled through magnetic field B as in bad to the bone at a constant velocity V, and that sets up this voltage. And this is just Ohm's law, no big deal. And you've seen this before, so that shouldn't be a big deal. All right, so we've learned about voltage before, and we know that an ideal battery is perfect. There is no internal resistance. But we also know that over a period of time, there is going to be internal resistance for that battery. And if we have an internal resistance, then it's going to not allow us to have as much voltage between the terminals, kind of like the friction inside the battery. And if we use a voltmeter on a battery, which we've done before when you've done the labs, then we know that VA minus VB is equal to the voltage of the battery minus the internal resistance times the current that it's draining. And there are several ways we can induce a voltage or an EMF. And the biggest help is to alter the flux, and we can change the magnitude of the magnetic field over time. We can change the area by physically altering the shape of the loop, stretching it, compressing it, or we can move it in and out of a magnetic field, or we can change the angle by spinning the loop. So there's lots of things we can do. As a result, we're going to have an induced EMF, and it's going to cause a current to flow, and the direction of the current is going to be determined by Lenz's law. And this is easier to learn if I just show it to you, but it's really not very hard. If you look at it, you have a bar magnet with a north pole moving into this coil, and as it moves toward the coil or loop of wire, the flux through the loop increases in the positive X direction because you're getting more field lines into that coil. The coil of wire must produce a magnetic field that opposes the change in flux by increasing flux in the positive X direction, so this coil has to set up a field that acts in the opposite direction. And next little bullet says, as the external magnetic field passes through the coil space, there's a magnetic flux through the coil because the fields are coming into the coil. And this external flux increases through the coil. And since there's a changing flux through the coil, there's going to be a voltage set up in the coil, which is going to make a current flow in the coil. And the induced current, the one we just talked about flowing in the coil, is going to make a magnetic field of its own. And it's going to be directed so that it opposes the change of the external magnetic flux. And so the induced current has to flow in this direction because it needs to generate a field in that direction. And we'll play with that a bunch because it's a little confusing while you're first learning it. Okay, if you look at this demonstration right here, in each of the above illustrations, the bold green arrow represents the direction of the external magnetic field. So it's increasing to the left in this diagram right here. So as a result, I need to have a current flow that causes a magnetic field to flow to the right, and that only happens if the current flows in that direction. If I look at this one, it is decreasing to the left, so I need to cause a current to flow that increases to the left to offset that change, so the current has to flow in that direction. Here it's increasing to the right, and you know what, no, I didn't. I guess this is decreasing to the right. Nope, can't tell what that is. Let's see. I'll have to look at that one. Let's move on down and see if we can figure out that one, what that is. Okay, so it is, it's just increasing to the right instead of to the left like it was up here. So it's increasing to the right. So I need to set up a current that will flow and produce a field that increases to the left. So there's the direction of my current flow. And then both of my, here I have, the very last example, I have a coil with a magnetic field getting smaller to the right. So I need to cause a field to be induced that increases to the right. And that's the direction that has to happen. Now, I said that all quickly. Stop it and study and look at what I've talked about, okay? But the key is if external flux increases, which it did here and here, it doesn't matter how this is accomplished, the direction of the induced magnetic field through the coil space will always be opposite to the direction of the external magnetic field. If the flux decreases, then the induced magnetic field needs to be in the same direction. And to find the direction of the induced current, determine the direction of the induced magnetic field. Remember that it is always opposite to the change in flux. Orient your right thumb along the line of the induced magnetic field, which is the bold blue arrow, and your fingers are going to curl around in the direction of the induced current. Okay. So we'll take a look at this. Determine the direction of the induced current through the ammeter when the bar magnet is moved left toward the coil. So if it's going toward the coil, it's causing the field to increase to the left. So I need to offset that by increasing a field or causing a field to increase to the right. And that makes my current move in that direction. Okay, if I go in the opposite direction, I move it away from the coil, then it's decreasing to the right. So I need a current that is going to create a field to the right. And to make that happen, I have to bring my current in the opposite direction. So let's see if what we're doing and what they're saying is going to make sense. The external flux in part A is increasing when the bar magnet is moved to the left. The only way to oppose an increasing magnetic flux is to produce a second magnetic flux that subtracts from the original. In other words, an induced current is needed that will produce a magnetic field in the direction opposite the existing magnetic field. Direct your thumb to the right and through the coil, and your right hands will curl so that the induced current will flow from left to right through the ammeter. The external flux is decreasing when the bar magnet is moved to the right. The only way to oppose a decreasing magnetic flux is to make a field that adds to the original. So an induced current is needed that will produce a magnetic field in the same direction as the existing magnetic field. Direct your thumb to the left and through the coil, direct your right thumb to the left and through the coil, and your right hand fingers will curl so that the induced current flows from right to left. Okay, I don't know where I was, so we're going to pretend that I was talking about part B. But if it is decreasing when the flux is decreasing when the bar magnet is moved to the right, then you need to increase it to the right. So your thumb of your right hand needs to point Yeah, I have a few issues with that one right there. We're going to go with what they have here because I feel pretty confident that I'm the one that's messing it up. All right. Now, we can induce a voltage if we move a bar through a magnetic field. This is a set of wires. And so I can have a complete circuit here. And what happens is as I move this to the right, then I have the flux increasing. And if the flux is increasing, then I know that I have an induced EMF, which is BLV. L is the length of the rod, V is the velocity at which it's being pulled, and B, L, and B are all perpendicular, so that's a sine of 90. And then the electric field within the moving conducting portion is simply E, electric field is equal to B times V. And an induced EMF generated by a coil of wire entering or leaving a magnetic field always generates a force that opposes the motion. If the coil is made to leave or enter the field, the induced current in the coil will interact with the external magnetic field, producing a force, F is equal to BIL. And that force will be opposite to the direction of motion, so that if it's being moved to the right, the force would be created to the left. Okay, so I'm going to work through these, and then we're going to talk about what's going on. Okay, so let me see if I can get my little pen. All right, so here's my coil of wire. I'm pulling it straight ahead, and as I pull it straight ahead, the amount of area of the wire that is exposed to the magnetic field remains constant, so there is no change in flux. Because remember, flux is equal to BA cosine theta. That does not change. That does not change. So there is no change in flux. So there is no EMF induced, 0 volts, and there is no current induced. All right, here what's happening is I'm pulling it to the right, and as I pull it to the right, the amount of area that remains in the magnetic field is decreasing over time. So there is a change in flux. So there is a current induced. And we said that if the flux is decreasing, then we need to induce a current that causes the flux to increase. So we need a magnetic field that's acting in the same direction as that magnetic field. So we're going to point our thumb into the page, and as a result, our fingers are going to coil in that direction. So that will be the movement of the current. If we go down to this next one, it's going to be this coil, or this wire is going to be pulled into, and that should be completed right there, into the field. So it's going to be increasing into the page. So I need to induce a current that will cause it to increase out of the page to offset that the change that produced it. So my thumb needs to point out of the page, and my finger needs to move, curl in that direction. So there's my induced EMF. Here I'm moving it along the edge of the field. There is no EMF induced, so there is no current induced, because the amount of field in the area are remaining constant.